theoretical notion called tree-depth, the tree-depth parameter. So in some way, the fact that the matrix is somehow sparse and contains a lot of zeros corresponds to the fact that its tree-depth parameter is small. Again, this is something which I will talk about later. So now for the motivation, and let me say just a few words formally about integer programming and fixed parameter algorithms. So integer programming is a well-known NP-complete problem. It's an optimization problem where the goal is to find an optimal solution to the system of linear equations. Formally, we want to minimize separable convex function f with this subject to ax equal to b, where A is called constraint matrix. This A, where the columns correspond to the variables and the rows correspond to the constraints we place on them. And this problem is known to be NP-hard, even for example, when f is a constant function, or when this constraint matrix A contains just zeros and ones. And recently, one approach how to try to solve this. So the research on integer programming has focused also on ways how to try to find fixed parameter algorithms that kind of try to work with the structure of the input matrix, that try to exploit its structural properties. So I mentioned that the main idea behind fixed parameter detectability is that apart from the input, in this case, the constraint matrix, you are given some more additional information that can help you to solve the problem more easily. Formally, an FPT algorithm is an algorithm whose running time is in the form of f of k times n to c, where f is a computable function and k is a fixed parameter independent on n. So, for example, this k can be the tree-depth parameter I mentioned before, speaking about the matrices, but it doesn't have to be just a numeric constant. For example, we can have a task, we can fix some graph G and ask whether it contains certain subgraph H. Then this parameter K can actually be equal to this subgraph H. I'm not sure whether you can see if I point something with the mouse. Is it visible for you? Okay, great. So let me further continue the presentation with an overview of a few important parameters of structural parameters related to graphs and matrices. I would like to start with tree weight, even though it's not that important for our result, but it's an important parameter both in structural graph theory and in theoretical computer science. So what's the motivation behind it? So as you probably know, that NP-complete problems are those for which no efficient solution is believed to exist. However, a lot of these problems actually become tractable when the input instance has some kind of restricted structure. For example, when it's an interval graph or when it's a tree. And the natural question is it possible also to extend this to graphs that are not, for example, trees themselves, but are close to trees or tree-like? And tree width is a formal way how we can capture this. Tree width is a measure that tells us how close the graph is to a tree. So I mentioned that it's quite important in graph theory. For example, it plays a key role in the graph miner series by Robertson and Seymour. And in theoretical computer science, it gained quite a lot of attention thanks to this theorem of Purcell, it's mentioned here, which says that if you have a class of graphs with bounded tree width, then every monadic second order logic property can be decided in linear time. So what is a monadic second order logic property? So in MSO, we can quantify not just over variables, but also over sets. So as an example of property that can be expressed, and as in MSO, we could pick a formula that would express whether the graph contains a Hamiltonian cycle. So you know this is an NP-complete problem, but actually if we have a graph that has bounded tree width, we can decide whether the graph satisfies this property of having a Hamiltonian cycle can be decided in linear time thanks to this theorem of Purcell. So let me now move to the parameter tree depth, which is more important, more related to our results. So tree-depth is in some way similar to tree-width, as it measures how close our graph is to a tree. But in this case, it measures how close it is to a special kind of tree. It measures how close it is to a star. So tree-depth is a more restrictive parameter than tree-width, as I mentioned before. And the bounded tree-depth implies that the graph is bounded tree-width. Informally, if a graph has a high tree-depth, then it means that there's a long path in it. So formally, we can define the tree-depth of a graph as a minimum height of a rooted forest, such that the closure of this forest contains the graph G as a subgraph. So what is a closure? So if I have a forest F, then its closure is the forest F when we add the edges from every node to all its descendants. Then the tree-depth is the minimum height such that the closure contains the graph as a subgraph. So for example here, on the left, let this be the graph G, then you can see that the minimum height of a forest that we could take such that closure contains our graph G would be equal to 4. We define height as the number of vertices, in this case, vertices on the longest path from root to leaf. So now we know what is tree-depth for graphs, but how is it related to integer programming, to constraint matrices of integer programming? So to define tree-depth for constraint matrix of integer programming, we first need to define a notion of dual graph. And the dual graph is a graph that we obtain from a matrix the following way. As the vertices, we take the rows of A. So for example, here for the matrix, we have 5 rows, so the graph will have 5 vertices. And 2 vertices I and J are connected by an edge in the dual graph if there exists a column such that ith and j's entries are non-zero. So for example, here you can see that by the first column, you see that the first, second, and fourth entries are non-zero. So that means that in our graph, the vertex corresponding to the first row, second row, and fourth row will be connected by edges. So then when we have the notion of dual graph, it's quite easy to define the tree-depth of a matrix. So then the tree-depth of a matrix is actually equal to the tree-depth of its dual graph. And the parameter of tree-depth has been recently studied quite well, and the research culminated with the theorem of Kotetzky, Levin, and on, who showed that integer programming is actually a fixed parameter tractable when parameterized by anti-complexity of the matrix and its tree-depth. But there's a slight problem with the tree-depth parameter. So let me try to illustrate it here. I'll go back to the initial motivation. We have here the matrices we had on the very first slide. Those matrices are row equivalent. But let's see what happens if you look at the dual graphs and try to compute their tree-depth. So if you look at the dual graph for the matrix on the left, you obtain a complete graph. For the matrix on the right, it's very sparse. And if you actually try to compute the tree-depth, then you will discover that for the matrix on the left, its tree-depth is 5, and for the matrix on the right, its tree-depth is 2. But here's the problem, because those matrices are row equivalent. But this means nothing else, that the tree-depth is not invariant under row operations. This is a serious drawback because the tree-depth is dependent more on the presentation of the matrix than on the true geometric structure of the problem. And we can have 2 matrices that correspond to the same instance of integer programming. But for example, in the algorithm by Kotetzky, Levin, and on, those would behave quite differently, as one has tree-depth higher than the other. And so that brings us to the main question of our research, of our paper, and that is there some parameter, or is it possible that integer programming is fixed parameter tractable with respect to some parameter that is invariant under row operations, parameter that would be the same for all row equivalent matrices? And the answer is yes, and here is where the matrix theory comes to play. So first, before I reveal what the mysterious parameter is, let me just define matroids, what matroids are. Matroid is a structure that tries to generalize some notions from graph theory and linear algebra. Formally, it's a pair X and I, where X we call the ground set and I is a family of independent sets. This I is a non-empty hereditary collection, when we require it to satisfy the following three conditions. So first we require that the empty set is always part of the family I. Then the second condition, if we have some set that is independent, that we require also all its subsets to be independent, so to be also present in I. And the third condition is so-called augmentation axiom that tells us if we have two independent sets, two sets in I, such that one is smaller, one is larger, then we can always find an element in larger of these sets, such if we add it to the smaller one, we obtain an independent set again. We can always extend the smaller set with some element from the larger and obtain an independent set again. So to make this more clear, I would like to mention two common examples of matroids, with the first being graphic matroids. So we can define a matroid on a graph. So as the ground set, we can take the set of all edges of the graph, and as the family of independent sets, we can take all the subsets edges that those sets are acyclic. Another example is the vector matroids, where as the ground set we can take a finite set of vectors over some field, and then the family of independent sets will consist of all sets of the vectors that are linearly independent. Okay, so now when we know, hopefully we know what the matroid is, we can move to the parameter of branch set. And actually this is the parameter that will help us to overcome the drawback of tree depth that I mentioned before. So before I define branch depth, I knew I need one more notion, and it is the notion of rank. So let X prime be some subsets of elements of the matroids, and then we can define that the rank of the subset of X prime is the size of the largest independent subset of X prime. But then we can define the branch depth of a matroid, so I define it for matroids, as a minimum depth of a certain decomposition tree of the matroid. And this decomposition tree is called depth decomposition. So what is the depth decomposition of a matroid? It's a pair that consists of a tree and the mapping. For the tree, we require that the number of edges of this tree is equal exactly to the rank of the matroid. And the mapping has to satisfy the following condition. So the mapping is between the elements of the matroids and leaves of T. So we map these elements of the matroid to the leaves of the tree. And we require the condition that if we choose any subset of elements of the matroid, then and look at the tree that is induced by the F images of this subset, then we require that the rank of the subset is at most the number of edges in the tree induced by this. So this is better to see on the picture. So if you, for example, see this leaf, these are binary vectors. So the rank of these three, of the subset of these three vectors is 2. And that satisfies the condition that if you look at the number of edges induced by this tree, that's 2. So it holds that the rank of this is bounded by the number of edges of this subtree. Similarly, for this leaf on the right, you can see that its rank is just 1, and the number of edges in the tree induced by the F image of this is 2. So it satisfies that the rank is at most the number of edges of this tree.
I have a question.
Mm-hmm. Yeah.
So by induced by the leaves, we mean like the minimum subtree that contains the root and these leaves?
Yes, exactly. Yeah.
Okay.
Mm-hmm. Yeah, thanks for the question. So yeah, so the branch depth then is the minimum depth of a certain tree that satisfies this condition for this matroid. And again, the question is how can we extend this to matrices and how is it related to integer programming? So if we have some matrix A as a constraint matrix of the instance of integer programming, then we can actually define a matroid on this matrix simply because we can take the columns of A as elements of our matrix as the ground set. And then we define that the branch depth of a constraint matrix of integer programming is equal to the branch depth of the underlying matroid. And the question here is this notion actually helpful? Does it satisfy the condition we want? Is it invariant under row operations? And the answer is yes, because it's quite simple to see, because if you have a matrix and you perform some operations that preserve row equivalence, then you don't change the space, and also the vector matroid defined on this matrix doesn't change. So all the matrices that are row equivalent actually have the same underlying matroid, and this means that also the branch depth, as it depends on the matroid, is the same for all matrices that are row equivalent, and the branch depth is invariant under row operations. So actually the branch depth parameter is the one that helps us to overcome the drawback of the 3-depth parameter. But before I summarize the result and show you some proof of why this worked, let me mention just a few algorithmic aspects of some graph and matrix parameters. I mentioned here 3-depth and 3-width for graphs. So for both of these, we have linear time FPT algorithms. For 3-width, it's an algorithm by Bodlander, and for 3-depth is the algorithm by Ryder, Rosmanet, Sanchez, Vlamel, and Sigtar. As for matroids, a lot of decision problems on these involve the parameter branch width, and rather than just giving here the definition, which is quite technical, let me just say that this is sort of analogous to the graph 3-width. And for this parameter, we have a cubic time FPT algorithm for computing optimal decompositions of matroids over finite fields by Hraniny and Ohm. And one of the goals of our paper was to decide whether there exists or to find an analogous result for the parameter of branch depth, as I've introduced it before. So we have shown that actually there exists an FPT algorithm for computing optimal decompositions of matroids over finite fields. So let me now summarize the results from our paper. So the first one is structural. So we have shown that the branch depth of a matrix is actually equal to the minimum G depth of a matrix that is so row equivalent to A. And the second result is that there exists an FPT algorithm that given a matroid M and an integer D, either says that the branch depth is more than D or computes an optimal decomposition of this matroid. And if we combine these two results together with the result of Kotetzky, Levin, and Ohm, that says that integer programming is fixed parameter tractable when parameterized by entry complexity and 3-depth, we obtain that actually integer programming is fixed parameter tractable when parameterized by entry complexity of the matrix and branch depth. So in the remaining part of my talk, I would like to focus on this algorithm, on the second result, and I would like to show you a brief sketch of how this algorithm works. So before I do this, are there any questions to the things I mentioned?
Maybe let me ask, is it easy to find the matrix which minimizes the 3-depth? Or does it follow from your results?
So I mean, how do we compute the matrix that has the minimum G-depth? Yes, this also follows from results. That if we are able to compute this, then we actually we can compute. One of our results is also that given a matrix, we can actually compute an invertible matrix B such that if we multiply A and B, then we obtain this matrix of minimum dual 3-depth. Yes, that follows from our result. And I'll mention it briefly later. Yeah.
Okay, thank you.
So to describe the algorithm, I first need to introduce a few tools that we needed to design the algorithm. So first, I need something called extended decomposition of a matroid. So formally, this is a triple T, F, and G, where T and F is a decomposition of a matroid as I introduced it before, so it satisfies all the conditions. and it's more enhanced by a mapping of G. So this mapping G is a mapping between non-root vertices of T, of the tree, and an arbitrary basis of the linear hull of the elements of the matroid. That moreover needs to satisfy the condition that if we take any element of the matroid, then we require that this element is contained in the linear hull of the G images of the vertices on the path from fx to the root. Again, this is quite complicated, so let me illustrate in the picture what it means. So, for example, when you look at the leftmost leaf, then if we take any of the elements mapped here by f, so for example the second one, then we require that it needs to be contained in the linear hull of the G images of the vertices mapped on the path from it to the root. So it needs to be contained in the linear hull of these two blue elements. These represent the mapping G. And moreover, we need something called principled decomposition, which is a special kind of extended decomposition, where we require that the image of G is precisely a subset of M. So image of G contains elements of the matrix, because here in normal extended decomposition, it can be arbitrary basis of the linear hull of the elements of the matrix. But here we require that we map precisely the elements that are present in the matrix. So these are the two main tools that we need for our algorithm. And now let me mention how it goes. So the starting point of our algorithm that given a matroid M and an integer D, either says that the branch depth is more than D or outputs the decomposition of the at most D. So the starting point is this approximation algorithm by Kadosh, Král, Libenau, and Mark from 2017. Which gets a matroid and an integer and either says that the branch depth is larger than this D or outputs a principal extended decomposition such that its depth is at most 4 to the D. So, and this is the starting point because based on the information we obtain by this approximation, the decomposition from this algorithm, we iteratively construct optimal decomposition or the decomposition of depth at most D iteratively in a dynamic programming way. So what we do, first we label the vertices, we take them in a way that the DF is transversal of the decomposition, this approximative one would give us. And for each of the vertices, we define sets AI and BI, where AI, as you can see on the picture, is the linear hull of G images of the left of U. So for example, if U is this vertex, then it's on the left, and BI is the linear hull of the G images on the right of UI. And so how the algorithm goes. So what we would like to do is we would like to iteratively, based on the information we have for each UI, construct some part of the decomposition. And to do this, I mean, we cannot do this in a naive way to store all the trees and the mappings because that would not be feasible and would not be an FPT algorithm. So to store the partial decompositions, we need something smarter, and for this we need something called frontiers. Let me now try to explain what a frontier is. The definition is quite technical, so I just want to mention here the intuition. So as I said, frontier allows us to store partial decompositions, already computed part of our decomposition we want to gain in an efficient way. So imagine that given two decompositions, T and T prime, and you can imagine that this T is the approximation of the decomposition given by the algorithm I mentioned, and T prime is the optimal decomposition we want to construct. Then the frontier is a subtree of this T prime that shows us how this red and blue part interact together in T. And the thing is that the frontier splits our decomposition into two parts. And if we have two decompositions with the same frontier, then we can take left part from the first one and right part from the second one, glue them together on the frontier and obtain a valid decomposition. And this is kind of the main principle of this dynamic programming algorithm we construct. So for each of these UI, as I mentioned, for each of these vertices in the way that the DOS transversal would output them, we compute the list of all possible frontiers of depth at most d. So first, so for each of these vertices, we have a list. Initially, for the first vertex, we have a list just containing one element, just the root and a null mapping. In each of the iterations, we iteratively compute list of all frontiers of depth at most d based on the list we obtained in the previous iteration. If the branch depth of matroid is more than d, then during one of the iterations, actually the list becomes non-empty, and we output this as a result that the branch depth is more than d. If the branch depth is less than d, then in the final list we obtain just one frontier, and from this one, what we do, we backtrack and construct a final sequence of frontiers, such that frontier is added in the final sequence if it triggered adding another frontier in the following iteration. So what we do, we obtain a sequence of 2R frontiers, of 2R parts of our decomposition, and from these frontiers, we finally compute or construct the decomposition of depth at most d. Yeah. So this was the algorithm that, given a matroid over finite field and some integer d, either tells you that branch depth is more than d or outputs the decomposition of depth at most d. From this follows that you can actually, given a matroid, you can compute the branch depth exactly, because what you can do, you can just run it for all the integers up to d and just take the minimum, and this will be the optimal depth decomposition that you want to obtain. And to answer the question that I had, whether it's possible to construct the matrix with minimum model tree depth, then this is possible because we are constructing here in this algorithm, we are actually constructing an extended decomposition. So we are constructing the decomposition together with the mapping that maps some element to each of the nodes of the decomposition. And then, roughly speaking, we then can use this mapping to construct an invertible matrix B, such that if we multiply our input matrix A with this B, we obtain a matrix A prime such that its tree depth is the minimum one possible. It's equal to the branch depth. So that was the summary of our results and the idea of the proof of the algorithm. So in the last 2 minutes, maybe let me mention possible directions for research, possible future work. So one of our results, actually in the paper, is also an approximation algorithm, very similar to the one I mentioned by Kardash and et al. So our paper also contains an algorithm that, given a matrix, also outputs an approximation, also outputs a matrix whose tree depth is at most 4 to the d of this matrix. And so one of the questions we are interested in is whether is it possible to kind of speed up this algorithm, because it's quite slow. The second questions that might be quite interesting are somehow related to this algorithm by Hryněny and O, as I mentioned. So I mentioned that for branch width, not for branch depth, but for branch width, there exists a cubic time FPT algorithm that computes optimal decompositions for matrices over finite fields. And the question is whether it's possible to construct a dynamic programming or fully combinatorial algorithm for this parameter, similar to the way as I presented the algorithm here, because the algorithm by Hryněny and on for branch width actually relies on the bound for size of x to the minus for matrix of bounded branch width What it does, the algorithm basically pre-computes all the excluded minors, and based on this, they construct the optimal decomposition for branch width. And the question is whether it's possible to construct an algorithm that would work, that would be more explicit, that would work in a dynamic programming way. Yeah. Yeah, so I think that's that's all for me now. So if you have any questions. Yeah, thank you.
I wanted to ask, so it seems, I don't know, did you say somewhere the bounds on the time complexity of your algorithm, of this one for the optimal depth width?
I don't remember the details precisely from the paper, but I think in the terms of because it's an FPT algorithm, so it's parameterized by branch depth. So then I think that branch depth is double exponential, and
yes, it seems so by the approximation.
Yeah.
And in terms of the input size? In
terms of the input size, I think it might be cubic in similar to the way of the algorithm for branch width.
Yeah, so I was wondering whether you tried to do some kind of iterative compression instead of this starting with this exponential approximation. This could somehow reduce the running time.
Yeah, no, it's an interesting thing, but no, we haven't thought about this this yet. Yeah.
I mean, I don't know whether there is a simple way, like if I give you just some rows of the matrix to add one more row and increase the size of the decomposition just by one or something like that, or the depth of the decomposition just by one. I don't see that whether this could be or couldn't be possible. But yes, that's what I was thinking. Like you have some decomposition and you're doing a better one. So maybe some iterative compression could be a way to go through this in faster manner. Yeah.
I agree, but I haven't personally thought about this in more. Yeah, but of course it probably there's some space for improvement regarding the complexity.
Okay.
Thanks. Are there other questions? It does not seem to be the case. So in that case, you should thank Kristýna once again and be glad for a nice talk.
Thank you.
Okay.